Today, we are mastering arithmetic sequences and series. In this lesson, you will learn to identify arithmetic patterns, calculate specific terms using the general formula, and find the sum of terms using various series formulae. You will also learn to handle sigma notation and apply these concepts to real-world contexts like simple interest and data approximation. This topic is fundamental to the IB analysis and approaches syllabus. It appears frequently in Paper 1 and Paper 2, often as part of larger questions involving financial mathematics or functions. Mastering these basics is essential for securing high marks in the early sections of your examinations. An arithmetic sequence is a list of numbers where the difference between consecutive terms is constant. We call this constant the common difference, denoted by the letter D. To find any term in the sequence, we use the nth term formula, where u sub 1 is the first term and n is the position of the term. The intuition here is simple. To get to the nth term, you start at the first term and add the common difference n minus 1 times. Let us apply this to a concrete example. Consider the sequence 5, 12, 19, 26, and so on. Our goal is to find the 20th term. First, we identify the first term, u1, which is 5. Next, we find the common difference, d, by subtracting the first term from the second. 12 minus 5 gives us 7. We can check this again. 19 minus 12 is also 7, confirming it is arithmetic. Now, we apply our general formula for the 20th term, meaning n equals 20. We have 5 plus 20 minus 1 times 7. This simplifies to 5 plus 19 times 7. 19 times 7 is 133, and adding 5 gives us a final result of 138. So, the 20th term of this sequence is 138. An arithmetic series is simply the sum of the terms in an arithmetic sequence. In the IB syllabus, you are provided with two primary formulae to calculate this sum, denoted as Sn. The first formula is S_n equals rac x n and 2 u sub 1 plus u_n. Use this when you know the first term and the very last term of the series. This works because the average of the first and last terms multiplied by the number of terms gives the total sum. Imagine pairing the first and last terms, the second and second to last, and so on. Each pair has the same sum. The second formula is S_n equals rac x n on 2. This is used when the last term is unknown. You might notice this is just the first formula with the nth term expression substituted in for un. It allows you to find the sum using only the first term, the common difference, and the number of terms. Let us calculate the sum of the first 50 terms of the sequence: 3, 7, 11, and so on. First, identify our known values. The first term u1 is 3. The common difference d is 7 minus 3, which is 4. Since we want the sum of the first 50 terms, n is 50. Because we do not know the 50th term, we use the second sum formula. Substituting our values, we get 50 divided by 2, multiplied by the quantity 2 times 3, plus 50 minus 1 times 4. This simplifies to 25 times the sum of 6 and 196. Multiplying 25 by 202 gives us 5,050. The sum of these 50 terms is 5,050. Sigma notation, represented by the Greek letter capital sigma, is a concise way to write a sum. Here is the general form. Sigma from r equals 1 to n of u sub r equals u sub 1 plus u sub 2 plus so on until u sub n. The variable at the bottom, r, is the index of summation. It tells you where to start. The number at the top, n, tells you where to stop. Let's look at an example. Evaluate the sum of 3r plus 2 from r equals 1 to 10. Notice that the expression 3r plus 2 is linear in r. In the IB syllabus, a linear expression inside a sigma notation always indicates an arithmetic series. To solve this efficiently, find the first and last terms to use our first sum formula. For the first term, we substitute r equals 1 into the expression. For the last term, we substitute r equals 10. Now, use the sum formula for 10 terms. S sub 10 equals 10 over 2 times the sum of 5 and 32. This simplifies to 5 times 37, which equals 185. The total sum is 185. This method is much faster than calculating all 10 terms individually. Arithmetic sequences have important real-world applications, most notably in simple interest. Simple interest is a calculation where the interest is earned only on the original amount of money invested, known as the principal. Because the interest added is the same every single year, the total value of the investment grows as an arithmetic sequence. The common difference, D, is equal to the annual interest earned. Let's look at an example. An investment of $1,000 earns 5% simple interest per year. Find the total value after 10 years. First, we calculate the common difference. 5% of 1,000 is 50, so the value increases by $50 every year. Crucially, the value at the start is 1,000. After 1 year, which we represent as U1, the value is 1,050. To find the value after 10 years, we find the 10th term of the sequence starting from the first year's end. The total value is $1,500. This shows how predictable arithmetic growth is over time. In real-world data, sequences are rarely perfectly arithmetic. When we look at experimental results or financial trends, the difference between terms might vary slightly. In these cases, we approximate the common difference by averaging the differences between consecutive terms. This creates a linear trend that represents the best fit for our data. Suppose we have the data points 10.2, 14.9, 20.1, and 25.0. To find an approximate common difference, we calculate the differences between each pair of terms. We get 4.7, 5.2, and 4.9. We then find the mean of these differences. By averaging these, we find an approximate common difference of 4.93, which we can then use to predict future values in the sequence. Let us work through an authentic IB-style question. An arithmetic sequence has a first term of 12 and a common difference of 6. The sum of the first k terms is 960. Find the value of k. First, identify our knowns. We need to find k, which represents the number of terms. Since we don't know the last term, we use the second sum formula and set it equal to 960. Substitute the values. Now we solve for k. We expand and simplify the bracket. Multiplying through by k over 2, we get a quadratic equation. Divide by 3 to simplify. This can be solved via the quadratic formula or factoring. Since k must be a positive integer, as it represents the number of terms, we discard -20. The value of k is 16. Always ensure your final answer for n or k is a positive whole number. In IB examinations, small errors can lead to a significant loss of marks. Let's look at how to avoid them. The first common mistake is miscalculating the number of terms in sigma notation. If a sum goes from r equals 4 to r equals 10, many students think there are 6 terms. Actually, there are 10 minus 4 plus 1, which is 7 terms. Always use the top minus bottom plus 1 rule. The second mistake is confusing the nth term with the sum of terms. Read the question carefully. Does it ask for the value of a specific position or the total accumulated value? Using the wrong formula will result in 0 marks for that part. Finally, be careful with the sign of the common difference. In a decreasing sequence like 10, 7, 4, the common difference is -3, not 3. If you use a positive d for a decreasing sequence, your results will be fundamentally wrong. To achieve a grade 7, you must understand how IB examiners award marks. Always write down the formula you are using and show the substitution of values. Even if your final calculation is wrong, you can often earn the method mark, known as M1, just for showing that you chose the correct formula and attempted to use it. Do not rely on memory. The IB provides a formula booklet, Use it to double-check that you haven't swapped a plus for a minus or forgotten the n over 2 in the series formula. In financial questions, such as simple interest, pay close attention to whether the question asks for the value at the start of year n or after n years. This often determines whether you should use n or n plus 1 in your formula. In paper 2, you can often use the summation function on your GDC to check your manual calculations for sigma notation. If your manual answer and calculator answer differ, recheck your work immediately. It is time to test your understanding. Please pause the video and solve these 3 questions. Easy. Find the 15th term of the sequence, 4, 11, 18, 25, and so on. Medium. Calculate the sum from r equals 1 to 20 of 5r minus 3. Hard. The third term of an arithmetic sequence is 7, and the 10th term is 35. Find the sum of the first 20 terms. Take a moment to work through these now. Let us go through the solutions. For the easy question, we identify the first term u1 as 4, the common difference d as 7, and the position n as 15. Using the nth term formula, u15 equals 4 plus 14 times 7, which is 4 plus 98. So the 15th term is 102. For the medium question, we find the first term by plugging in r equals 1, giving us 2. The 20th term is 5 times 20 minus 3, which is 97. Here, n is 20. Using the first sum formula, the sum of the first 20 terms is 20 over 2 times the sum of the first and last terms. This calculates to 10 times 99, giving a final sum of 990. For the hard question, we use simultaneous equations. We know the third term is u1 plus 2d equals 7, and the 10th term is u1 plus 9d equals 35. Subtracting the first from the second gives 7d equals 28, so the common difference d is 4. Substituting d back to find the first term, we get u1 equals negative 1. Now, find the sum of the first 20 terms. Using the formula, s20 equals 10 times negative 2 plus 76. This simplifies to 10 times 74, so the sum is 740. To summarize our lesson on arithmetic sequences and series, 1. The common difference, d, is the constant value added to each term. 2. Use un equals u1 plus n minus 1 times d to find specific terms and Sn formulae for sums. 3. Linear expressions in sigma notation represent arithmetic series. Find the first and last terms for quick calculation. 4. In real-world data and simple interest, identify u1 and d carefully to model growth accurately. 5. Always show your substitution in formulae to secure method marks in your IB exams.